Good day everyone. In this video we will see what is center of gravity and effects on kg due to change in center of gravity when a mass is added, subtracted or shifted on board a ship. Let's see the application to a ship when discharging, how the center of gravity is affected. Here GG1 denotes shift of center of gravity of a body. Now let's see the same with an example. When mass small w is removed from the lower part of a ship, the center of gravity will shift directly opposite to a point GG1 as shown in the figure. Now let's take another case where a weight W is removed from upper side of a ship. How the center of gravity will move towards the lower side of the ship. Further, let's see in the diagram the movement of center of gravity diagonally when mass is removed. Next, let's see in the diagram the movement of center of gravity horizontally when the mass is removed from a vessel. So on the basis of the diagrams which we have seen, we come to the conclusion that when a mass is removed from a body, the center of gravity of the body will move directly away from the center of gravity of the mass removed. As we know, moment is defined by the formulas below. Moment is equal to W into D, and also moment is equal to W minus W into G1. Therefore, the final formula derives Gg1 is equal to small w into d divided by big W minus small w, where Gg1 is the shift of center of gravity of the body, W is the mass removed, d is the distance between center of gravity of the mass removed and center of gravity of the body, W minus W is the final mass of the body. Similar to discharging, now let's see the application to a ship while loading. That is, when mass is added to a ship, how the center of gravity shift to upper side, lower side, diagonally and horizontally. In case of loading, the formula Gg1, that is the shift of center of gravity of the body, changes with the denominator as W plus W, that is the initial mass of the body and added weight onto the body. Here in the diagrams we are looking at the shift of center of gravity vertically, diagonally, and then will be seen on the horizontal axis. Coming to conclusion, when mass is added to a body, the center of gravity of the body will move directly towards the center of gravity of the mass added, where Gg1 is equal to small w into d divided by big W plus small w. Further ahead, after addition and subtraction of weights on a ship, now let's see the effect on center of gravity when weights are shifted on a ship in the following diagrams. Here the center of gravity changes from G to G1 and sets finally at G dash. So the conclusion, when a mass is shifted inside a body, the center of gravity of the body will move parallel in the same direction of the shifted mass with a distance of g(g1), while g(g1) is equal to small w into d divided by big W. Finally, concluding all three conditions: first, when mass is loaded; second, when mass is removed; and third, when mass is shifted from a body, the formulas as described will be applicable. That is, when mass is added, gg1 is equal to small w into d divided by big W plus W. When mass is discharged, gg1 is equal to small w into d divided by big W minus W. And when mass is shifted, gg1 is equal to small w into d divided by big W. Let's now discuss final kg. Now consider that we are loading and discharging several masses and we would like to calculate the final kg of the ship. Well, it's not logic to calculate gg1 for each load and then calculate the final kg of the ship and repeat the same for each load separately till we reach the final kg of the ship after completing loading and discharging all the masses. So, the correct way to calculate the final kg of the ship after loading and discharging several masses is to take the moments of all masses loaded and discharged, including the mass of the ship about the keel of the ship, then calculating final kg by dividing the total moments by the total mass, the final displacement. Hence, final kg is equal to final moments divided by final displacement. The builder of the ship provides the ship with the stability booklet containing all the stability information of the ship, that is, lightship, the lightship kg, and LCG, the position of center of gravity of cargo holds and tanks. So now let's see some numericals and their solutions related to kg. Question number 1. A vessel of 8,000 tons displacement km 9.2 meters and assumed to be constant kg 8 meters loads the following: 500 tons kg 4.0 meters, 800 tons kg 9.0 meters, 700 tons kg 7.2 meters. The vessel then discharged the following: 400 tons kg 1.6 meters, 200 tons kg 6.0 meters. Now calculate the amount of statical stability when the ship is heeled by 8 degrees. So now let's see with the help of diagram how to solve this numerical. So initially we have vessel with 8,000 tons of displacement kg 8 meters, and now the following weights 500 ton, 800 ton, 700 tons are added. On the other side, the weights 450 tons, 200 tons are subtracted with their respective kgs. Now let's see the table with weights, their kgs, and the moment about the keel for all the weights available. That is 8,000 initial displacement with 500 tons added, then 800 tons added, 700 tons added, 450 discharged, 200 tons discharged with their kgs. Now let's calculate the moment about the keel for these weights as follows. The initial weight and the weights added will be with plus sign and the weight subtracted will be with minus sign to calculate final displacement. Similarly, for the moments about the keel, to calculate final moments. So now let's calculate kg final with formula final moment divided by final displacement, that is 76320 divided by 9350 is equal to 8.16 meters. That is gm final is equal to km minus kg final. Hence we have gm final is equal to 9.20 minus 8.16 equals to 1.04 meters. To get the moment of statistical stability, formula W into gm into sine theta, where W is final displacement, gm is gm final, and sine theta, where theta is heeled angle, that is 8 degrees, we get the moment of static stability is equal to 1366.62 tons meter. Similarly, let's see question number 2. A vessel of 13,000 tons displacement kg 9.5 meters loads 400 tons of kg 2.9 meters, 900 tons kg 6 meters, 1500 tons kg 10.6 meters, 300 tons kg 8.3 meters, and then she discharges 700 tons kg 1.5 meters, 300 tons kg 12.7 meters. Calculate the moment of statistical stability if the ship has 8-degree heel, km given as 10.5 meters and assumed to be constant. So here the similar way we calculate the moment of statistical stability. So we find the final displacement, final moments, and then kg final with formula of final moment by final displacement, that is we get a value of 9.5 meters. Gm final is equal to km minus kg final, hence gm final 0.99 meters. Moment of statistical stability is equal to W into Gz, which is equal to W into Gm into sine theta. By putting the value, we get answer as 2100.95 tons meter. Number 3. A ship of 3000 tons light displacement and light kg 6.4 meters has to load 9600 tons of cargo. The kg of lower hold is 4.5 meters and that of the tween deck is 9 meters. The load km is 6.2 meters and when loading is completed, the righting moment at 6 degrees of heel is required to be 425 tons meter. Calculate the amount of cargo to be loaded into the lower hold and tween deck respectively. Righting moment is equal to W into Gm into sine heel. So we have to load cargo of total 9600 tons. So let's assume X tons is loaded in lower hold with kg of 4.5 meters. Hence, in the tween deck, it is loaded 9600 minus X tons with kg of 9 meters. The initial displacement of the vessel was 3500 tons and kg of 6.4 meters. Righting moment formula is W final into Gm final into sine theta. So we need a righting moment of 435 tons meter. W final, that is final displacement 3500 tons plus weight added 9600 tons is equal to 13100 tons. Gm final into sine theta, that is sine heel of 6 degrees. Hence we get the value of Gm final, that is 0.31 meters. Putting the value of km and Gm final, we can find out the value of kg final, that is 5.89 meters. Now assume the weight of cargo in lower hold as W, which was X in the diagram, and in tween deck it will be 9600 minus W. Hence putting all the values, we get final displacement as 13100 and the final moment as 108800 minus 4.5 W. Hence putting these values in the formula below, we can find out the value of W, that is weight in the lower hold, and then in tween deck. Next question. State and explain the formula of calculating KB, transverse and BM for a vessel at a particular draft. Part 2. Calculate the change in transverse metacentric height GM of a box shaped vessel on even keel of 20 meters, beam and salt water draft 7 meters on passing from RD 1.025 to water of RD 1.000. To find Kb, the center of buoyancy is the center of gravity of the underwater volume. For box shaped vessel on an even keel, the underwater volume is rectangular in shape and the center of buoyancy will be the half length on the central line and the half at the draft. Therefore, for a box shaped vessel on an even keel, Kb is equal to half the draft An ordinary ship, Kb can be obtained from any draft from the hydrostatic data, and close approximation of the depth of center of buoyancy from the waterline can be obtained by using Morrish formula, where the depth of center of buoyancy below water level is equal to 1 by 3 into d by 2 plus V divided by A, that is volume divided by area. To find the transverse Bm is equal to I divided by V, where the second moment about center of line I is equal to LBQ divided by 12. Putting these values together, we get for box shape vessel Bm is equal to LBQ divided by 12V. Hence, Bm is equal to P square by 12D. So now the part B, calculate the change in transverse metacentric height of GM of a box shaped vessel on even keel of 20 meters, beam and a saltwater draft of 7 meters on passing from water of RD 1.025 to water of RD 1.000. Now using the formula Km of saltwater is equal to Kb plus Bm, and Gm is reduced by Km saltwater minus Km freshwater. Also Kb is equal to draft by 2 and Bm is equal to B square by 12D. So we get the values, and hence we put the values and get Kb is equal to 3.5 meters, Bm is equal to 4.7619, Km saltwater is equal to Kb plus Bm, that is 8.2619 meters. Now as we know that when a box shaped vessel passing through water of different densities, then the formula which applies is old draft into old density is equal to new draft into new density. Hence, putting the values old draft as 7, old density 1.025, new draft D and new density 1, we get value of new draft is equal to 1.175 meters. Thereby, when ship is floating in fresh water, the value of Kb is equal to D by 2, we get 3.875 meters, K value of Bm 4.6457, and value of Km freshwater is equal to Kb plus Bm as 8.2332 meter, and Gm is reduced by Km saltwater minus Km freshwater, that is 8.2619 minus 8.2332 is equal to 0.0287 meters. Question 3. A box shaped vessel, length 100 meters, beam 12 meters, depth 10 meters is floating on a draft of 6 meters in salt water. kg 4.5 meters. Calculate the following: A. Metacentric height. B. Moment of statistical stability when heeled 20 degrees. C. Moment to change the trim by 1 centimeter. D. The tons per 1 centimeter immersion. So with formulas Kb is equal to D by 2, we get Kb is equal to 3, Bm is equal to B square by 12D, value is equal to 2 meters, Km transverse is equal to Kb plus Bm is equal to 5 meters, Gm is equal to Km minus Kg is equal to 0.5 meters. B. Gz at 20 is equal to Gm plus half G into Bm tan square theta into sin theta. Putting the values, we get answer 0.216 meters. W is equal to length into breadth into draft into water density, that is W displacement is equal to 7380 tons. Hence moment of statistical stability is equal to W into Gz, hence value equal to 1594.08 meter tons. Next, to calculate tons per centimeter immersion, that is TPC, first we calculate BML by formula L square by 12D. KML is equal to KB plus BL. GML is equal to KML minus KG. MCTC is equal to W into GML divided by 100L, and thereby putting all these values and answers in TPC is equal to A into 1.025 divided by 100, we get answer as 12.3 tons as TPC. Here BML is BM longitudinal value 138.89 meters. KML is KM longitudinal equal to 141.89 meters. GML GM longitudinal equal to 137.39 meters. MCTC is equal to displacement into GM longitudinal divided by 100 into length of vessel equal to 101.394 meters. Thereby we get the TPC as 12.3 tons. Next question. A pontoon of constant rectangular cross section is 42 meter long, 7.6 meter beam, 4.26 meter depth, and floats in seawater at draft of 1.52 meters with its center of gravity 1.98 meters above the base. Determine the greatest load which can be added at a height of 4.26 meters above the base without causing the pontoon to become unstable. As we know, W is equal to length into breadth into depth into water density. Thereby 42 into 7.6 into 1.52 into 1.025 is equal to 497.3 tons. D is equal to 4.26 minus 1.28 is equal to 2.28 meters. Thereby the quantity to load is equal to weight. In order to load the maximum weight, then GM is equal to GG1. As we know, Gg1 is equal to small w into d divided by big W plus W. Also, Kb is equal to draft by 2 is equal to 1.52 divided by 2, 0.76 meters. Bm is equal to b square divided by 12d, where b is equal to 7.6 square divided by 12 into 1.52 is equal to 3.167 meters. Km transverse is equal to Kb plus Bm equal to 0.76 plus 3.167 is equal to 3.927 meters. Thereby Gm is equal to Km minus Kg is equal to 3.927 minus 1.98 is equal. So to load maximum Gm is equal to Gg1, thereby 1.947 is equal to small w into 2.28 divided by 497.3 plus w. Thereby putting these values we get value the weight to be added. W is equal to 968.24 divided by 0.333 is equal to 2907.6 tons. That is, the greatest load which can be added at height of 4.26 meters without causing the pontoon to become unstable is 2907.6 tons.